So today we're going to talk about the multiple rules on combinatorics, how to calculate different types of combinatorics. Okay, something wrong. So we will visit several cases, very interesting cases about combinatorics, and we'll start from the very basic one. But let's consider a outcome of an experiment. Okay. But this outcome has several trials, several independent trials. Let's say we have this is the first trial, this is the second trial. Okay, the first trial, second trial, third trial, fourth trial. Suppose we have R different trials. Okay, you can think of this as, for example, flipping a coin repeatedly for R times. Okay, every time is kind of independent. So this is the trial. And for every trial, we assume that we can observe. For example, for the first trial, we assume that there might be N1 different possible outcomes. Okay. And in the second trial, when you in the second trial, you can observe N2 different outcomes. So in every single trial, you may observe a different number of different outcomes. So the question is, for this entire for this entire outcome, how many number of different outcomes do we have, considering all these different trials? Right? Every trial, the ICE trial, have Ni different outcomes. So this is the basic combinatoric problem. Well, the basic rule is to multiply everything together, because every single outcome in each trial, in every single trial, is possible to be combined with all the other outcomes in all the other trials. So the total number of different omega is given by the first trial has N1 possible outcomes. So the second trial has N2, so we multiply them together. These are all the possible combinations for the first two outcomes. Okay, and we keep doing that. Okay, so this is the total number of possible outcomes for this repeated experiment. So this is a multiplicative rule. And let's consider some more specific examples or questions. Okay, questions Q1. So consider the following question. So we want to look at the number of ordered lists of N objects without replacement. Okay, so what does this mean? So we have N objects. Let's denote them as N different balls. Okay, we have n different balls, and we are going to place, we are going to order these n different balls in an ordered list without replacement, meaning that every ball we are going to sample it. Once we sample a certain ball, we will never put it back. Okay, so every ball will be used only once. So basically, we are going to place n different balls into n positions, and these positions are ordered. The order of these positions may be different depending on which ball you place into a certain position. So the question is, once you place these n different balls into these positions, how many possible different ordered lists can we have? So any ideas? So basically, you are going to start with, you can calculate this the number of different order lists by following this process. If you want to place n different balls into n different positions, you are going to start with a certain ball, right? Let's say you pick any one of them. Let's say you start with 3. Okay. Suppose these balls are in a, you put them in a black box and you randomly grab one, let's say 3, number 3, and you are going to place it somewhere in these positions. Now, how many different how many different choices do you have for this specific ball? When you place the first ball, how many choices do you have? Yeah, you have n, right? N different choices. And you put it somewhere, let's say you put it in second place. Right. And then you are going to, and now you have used this ball 3, so it is removed from this black box, right? And then you do this again, you grab another ball randomly, maybe the last one, and then you are going to place this ball into the rest of the places. Now this time you can see that we only have n-1 choices, right? And then you place it here, and then you do this repeatedly. You grab the third ball, and you realize that you only have this many positions left. Okay, and you keep doing that until you reach 1. Okay, so once you have placed n-1 balls into their positions, the left one, the last one, you only have 1 position left. So that is the only possibility. So this is the total number of ordered lists that we can have when we place n different objects into different positions. So their order, so every different order of these n objects corresponds to one different outcome. So we denote this as n factorial. So basically, as you can leverage this rule in the homeworks or the exams, right? Whenever you want to deal with placing n different objects into n different positions. So for example, we can consider how many distinct numbers can be obtained from these 9 digits. Okay. And every digit, we are going to use them exactly once. right? We have 9 digits, and we're going to, so basically you are going to order these 9 digits in different ways to create different numbers. And apparently, according to the previous order release rule, we have 9 factorial, this many number of different numbers. Okay, because every time you order these 9 digits in a different way, it's going to be a different number corresponding to a different number. Okay, so in the first question, we care about we have n objects, and we are going to place them into exactly n positions, right? So a more general scenario is that you have many objects, and you only have a few positions. So you are going to select a few objects from this set of objects and place them into those few positions. So this is the second question we want to consider. Again, we are going to look at the number of ordered list of k objects selected from n objects. Without replacement. Okay, so again, we have n different objects, but now we only have k positions. Okay, and this k is less than n. We don't have few positions. So what we are going to do is to grab k different objects from this black box, like k different balls from this set, and then place those k different balls in an ordered list. And then we are going to ask how many different number of ordered lists can we have. So the challenge for this problem is that, first of all, you don't know which k balls you select in the first time, right? Okay, so in the first stage, you want to select k different balls out of n different balls. So you have to figure out how many ways can you have to select those k different balls. And then in the second stage, you are going to order the selected k number of balls into an ordered list. So here we can fill all these positions by following the following process. We basically, again, we follow the same process as what we did in question 1. We basically grab one ball and place it into these positions and fill these positions one by one. Okay, so let's say okay, so I'm going to fill this, but I'm going to fill the first position out of these k positions, and I have n different balls to choose, right? So in the first stage, the number of choice I have is n. It's number n. Right? I can choose any of these n objects and place it into this position. Now, suppose you select 3. You have n different choices, and then you are going to fill the second position. And this time, now the first one, this ball has been used, so you only have n-1 balls left. So here you have n-1 choices. Okay. Maybe you place 7 here, and then you keep filling these positions, right? So every time the number of choices will be decreased by 1. But you only have, in total, you have k positions. So you only have k terms, right? This is the first term, second term, third term. So the kth term will be n minus k plus 1. Right, this is the kth term. So once you fill in the kth position, you only have this many number of choices, this many number of balls left. And you can verify that this is n factorial divided by n minus k factorial. And we usually denote this as using this notation, PNK. P stands for, so N and K stands for that we are now choosing K objects out of N objects. And P stands for permutation. So because here we are looking at the order list, so the positioning of these K objects is critical. Okay, so this is just a notation, but this always means that this always corresponds to the statement of this question. Okay. Out of N objects, we are choosing K objects and place them in an order list. And the total number of this order list is given by P and K, which is N factorial divided by N minus K factorial. Yes.
How do you, like, I get it, it's like a permutation, but how do you go from N, like that top?
This one,
That was up to
these two.
yeah, how do you go?
Yeah. You basically you can add, okay. You can introduce additional factors. Okay, so you keep doing that until you reach 1. But to make everything equivalent, you need to divide it by the same number of factors you introduced. Yeah. And the numerator, you can see, starts from N and goes to 1. This is exactly N factorial. And the denominator is exactly N minus K factorial. Yeah. So we usually write it in this way because it's much simpler. Or you can just say P and K. Right, so here we are talking about choosing K objects from N objects and then placing them into an ordered list. So the positioning of these objects matters. Right? And in many cases, so the next question, in many cases, we need to deal with the scenario where we only care about choosing K objects from out of N objects. And we do not care about the positioning or the order of this among these K objects. So this is for question 3. So the number of sets of K objects out of N objects without replacement. Okay. So here we are talking about, again, we have N objects and different objects. And out of these N objects, we are going to pick a subset of K objects But we don't care about different from Q2. In Q2, we care about the order, the positioning of these K objects. But here we do not care about the positioning anymore. We only care about the set that you picked. For example, suppose you have n different balls. Okay. Now suppose you pick the ball 2, 1, and 3. Now this will be the same as picking 1, 2, and 3. They are the same for this question because we only care about the set that you selected. We don't care about their positioning. Right? So this different, the permutations among the same set of K objects will be regarded as the same thing. We don't care about the positioning, the ordering anymore. Okay, so the question is how many different such sets can we select out of this n objects? Right. So think about this. This is somewhat related to question 2, right? Maybe we can stand on question 2 and try to figure out question 3. In question 2, we know how to compute the number of ordered list of K objects. Okay. So in question 2, these 3 scenarios will be treated as different ordered lists because although this list contains the same number of elements, the same set of elements, but their ordering is different, right? And in question 2, we care about ordering, so we will count these 3 different scenarios as different cases. But in question 3, we no longer care about the permutations among these K objects. So we can just take the number that we get from question 2. Now this is a total number of all different order lists of length K. And we are going to divide it by the repetitions that we consider in question 3. That is all the possible permutations among these selected K different objects. So how many permutations do we have? Is the K factorial. Okay. Right. So in the numerator, this number is given by the total number of ordered lists of length K. But then for every ordered list of length K, you have this many number of possible permutations, right? So you have to, in order to removing those redundant permutations among these K objects, you are going to divide it by K factorial. Okay. Because in this case, all different permutations among these K objects are treated as the same thing. So we are going to use division. We're going to divide it by all the possible number of permutations within these K objects. So this is the final result. And it is given by the Pnk is given by this one, and we're going to divide it by K factorial. So we call this Nk. This is notation for this one, without permutation. In this case, Nk means that we only care about the set of K objects that you selected. We don't care about the ordering among these selected objects. Okay, so this is how you calculate this the number of different selections. So you see that comparing Q2 and Q3, the only difference is that whether or not you care about the ordering among the selected objects. But if you care about ordering, then you use P and K. If you don't care about ordering, you use NK. So consider an example. Consider repeated N Bernoulli trials. We have N trials. Each trial is the Bernoulli trial. Bernoulli trial means that for every trial, the event E happens with probability P, where its complement happens with 1 minus P. Okay. For example, you can equivalently treat this Bernoulli trial as flipping an unfair coin. Okay. The head, you have P probability to get a head, you have 1 minus P to get a tail. And you do this for N times, okay? So we're looking at the probability that K occurrence of event E in this trial, in this N Bernoulli trials. Okay. So out of N repeated trials, what is the probability that we observe K occurrence of event E, right? So for every outcome, you will have N different positions, right? You have N different trials. For each trial, you may have E or E complement. Okay. So you have so many different number of combinations. But how many different number of combinations do we have? Each position, we have 2 possibilities. So it's 2 to the power of N. We have this many number of outcomes. And we want to look at what is the probability that among these N trials, we will observe exactly K occurrence of the event E. Okay, we have K of them. And we have, for E complement, we have N minus K, right? So in total, we have N trials. If we observe KE, then we will observe N minus K E complement. So the first question is, how many possibilities, how many different number of outcomes do we have corresponding to this event? Among N different trials, we have exactly K number of E. How many combinations do we have? So shall we consider Q3 or Q2? Well, from the statement, we only care about the number of occurrence of E. We don't care about where they are, right? So as long as these N positions have K number of E's, then we are good. So we simply use choosing K from N. Right? Because we don't care about the ordering, the positioning of these occurrences. Right? So we using this one, this denotes that we have this many number of outcomes that has exactly K number of E's in it. Okay, so it's basically choosing out of these n positions, I choose K of them and place a E into those K positions. Okay, so we only need to choose K positions out of n. So think about this. Once I selected K positions out of n, and that's it. I just need to fill in those K positions by with E, and the rest of positions with E complement. That gives a proper outcome of this event. Right? And selecting K positions out of n is a combinatorial problem of Q3, right? We only care about selecting K objects out of n objects. We don't care about the ordering among these selected K positions, because we will place all of them will be filled with E, the event E. Okay, so the ordering doesn't matter. We only care about the number of occurrence. Okay. So once you specify that, this is the number of different outcomes that has exactly KEs in it. Okay. So you have K positions have E in them, and n minus K positions have E complement. And you can, and because each trial is independent, so you can calculate them independently. So each E happens with probability P, and you have K of them. So you repeatedly multiply P by K times. Okay. And each E complement happens with probability 1 minus P. And you have n minus K of them. Okay. So you repeatedly multiply them n minus K times. So this is the probability of each outcome of this event. Okay. Whenever you see K number of E and n minus K number of E complement, this is the probability, because all the different trials are independent. So this is the same for all different outcomes in this event. And this is the total number of such outcomes that belongs to this event. Okay. So the final answer is, first you choose K from N, but this gives you the total number of different outcomes that belongs to this event. And then you specify the probability for each outcome. So this is a distribution for this event. You can, depending on the value of N and K, by this distribution will behave differently. So whenever you see such a statement like K occurrence in unrepeated trials, okay, this means that, well, K occurrence, I just need to select K positions out of N and then specify those K positions with the occurrence of E. And that's it. For the rest of N minus K, they have to be E complement. And how many such positions can I select? Well, this is a problem of in the form of Q3, where selecting K objects out of N objects. But we don't care about the order of those positions. So I just select K from N. Okay. But once I specify that, I just need to calculate the probability of each possible outcome. And for each outcome in this event, we have K occurrence of E and N minus K occurrence of E complement. So K occurrence of E is given by P to the power of K. Okay. And N minus K occurrence of E complement is given by this one. So both parts are necessary. Okay, and you can actually verify that you can verify that this is a proper distribution, because if you sum over K, if you sum this probability over K, you get exactly 1. Well, K starts from 0 to N. Okay. Why? Because out of N trials, you can either have 0 occurrence of this event. You can either have 0 head, 1 head, 2 heads, 3 heads, up to N heads. One of them must happen, right? So once you sum them up, it has to be probability 1. And if you do this, if you calculate this, if you sum up these probabilities, indeed they sum up to 1. Well, because this includes all the possibilities, right? This means that out of N trials, how many occurrence of out of N flip of coins, right? How many heads can you observe? Well, either you can observe 0 heads, or 1 head, or up to N head. Those are all the possible outcomes, right? So when you sum them up, you must get probability 1, because that covers everything, every possible case. Okay, now here we look at the following question. So we have T different types, T different colors of T different types of balls. Okay, each type of ball has different color. Right. And for each type of ball, we have Ki of, for the ice type of ball, we have Ki of them. So for this black one, we have K1, red one, we have K2, and blue one we have KT. Maybe you have many different other colors. And this K, so in total we have N of them. Okay. And for the balls that are in the same type, they are indistinguishable. So the red balls, they are exactly the same with each other. They are indistinguishable from each other. Okay. So basically we have in total N balls. We have K1 black balls, K2 red balls, and KT blue balls. Right? Every type of ball, the balls of the same type are indistinguishable. Okay, what do we want to look at? We want to look at the number of different arrangements of all these balls. So you place all these N balls in N positions. Right? You place all these N balls in N positions. How many different number of arrangements do we have? And in this case, note that the balls that fall into the same type, they are the same. Okay. So that means if you switch the position between among balls that have the same color, it does not change this arrangement. But we only care about the order across different colors. Right? And for this type of problems, we always relate them to the previous types of problems that we have looked at. Okay. And try to decompose the problem into smaller problems. For example, here, apparently the challenge is that, well, previously we know how to arrange N different balls into different positions. Okay. If you look at Q2, okay, actually Q1, we have N different balls. We're going to place them into N different positions, and we care about the ordering. Okay, for this one, we know it's P and K. It's given by P and K. Okay, it's actually by P and N, which is N factorial. But now, in this case, only the balls with different colors are treated as different balls. Right? The balls with the same colors are indistinguishable. So we have to remove the redundant permutations created by the permutations within the balls that have the same color. So I can do the same thing. I can do the following. I can assume that at first these balls, I give them different labels. I assume that everything is different. Okay. And then I place these balls into this ordered list. So I would have this many number of possible ordered list. But then I look at the balls that have the same color, like these balls, black balls, they will be placed somewhere in this list. And I know that they are actually indistinguishable. So I need to divide this total number of permutations by all the possible permutations among these black balls. Because, right, they are indistinguishable. They don't have these labels actually. So you need to divide them by K1 factorial. This is the total number of permutations among black balls. And then for red balls, it's the same thing. The permutations among red balls are treated as the same list, right? So you need to divide it by all the possible number of permutations among the red balls. And until you divide it by all the possible permutations among the blue balls. Okay. So this is how you get this result. You first assume everything's different. So this is the total number of ordered list. But then actually the permutations among these different colors, among the balls that have the same color, is actually treated as the same order. So you just divided all the cases by these different factors. So for example, we can apply this to calculate the number of arrangements we can calculate the number of arrangements of these letters. Okay, these letters are carried from probability, and each different letter can be treated as can be understood as a ball of a different color, right? And so here we have, some letters are repeated. We have 2B, 2I, and the rest of the letters, I think they are just have one of them. So the number of arrangements means that we have 2Bs, right? Once if you switch the positions among these 2Bs, they are the same, right? They does not change the arrangement of all these letters. So in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. And we have 2B and 2I. So the total number of arrangements is that I first treat these 11 letters differently. So in total, we have this many number of ordered list. Right? And then I consider the permutations among the same type of letters. We have 2Bs, so we have, I need to divide it by 2 factorial. And we have 2 Ls, 2 Is, I need to divide it by 2 factorial. This is the total number of different words that you can create from these letters. The rest of the letters, they only appear once, so 1 factorial is just 1, so it doesn't change the result. So you only need to consider those letters that are repeated more than once. Okay. So this is about this problem. You have multiple types of objects. Each type of objects have multiple elements in it. And then we consider the ordering among these objects. Okay, the last one. I mean, all these different combinatorial problems, they are actually very common, right? We'll see them. If you look at each problem, it looks a very, very reasonable problem in the daily life. And the last one is, again, another very interesting combinatorial problem. So you have an indistinguishable objects and we want to put them into K distinguishable boxes, let's say, boxes. For example, you may have five balls. They are exactly the same. They are indistinguishable. You want to put them into 3 boxes. And these boxes are distinguishable. Each box has different label. Now, how many different ways can you do this? For example, you can put 1 ball in the first box, 2 in the second box, and 2 in the third box. And we only care about how many number of balls do you place in each box. And think about how can we approach this problem. Well, this is a very, very common problem in daily life. You have n different apples, n indistinguishable apples, you put them into k different boxes. Okay, how many different ways can you do that? If you start from the first box, now can we do the following list? Well, if we start from the first box, we have, even for the first box, we have so many different ways. Could be 0, could be 5, up to 5, right? And for each different, once we specify the number of balls that we put in the first box, then we know for the rest of 2 boxes, we know the total number of balls that we put into the rest of 2 boxes. But then we need to further discuss the scenarios, that how many balls do we put into second one and third one. So it seems that we will have so many different scenarios. And for each scenario, we have to discuss it one by one. So this will be a very tedious process if we go this one by one. And here's a very, very convenient reformulation of this problem. Okay. So I claim that in order to place 5 apples into 3 boxes, I just need to somehow cut them into 3 different chunks using 2 separators. For example, if I put two separators here and here, then this will be the first box, second box, and third box. So depending on how I place these two different separators, I can create a different realizations of the number of apples that I put into different boxes. Like for example, if I place the separator here and here, that means first box and second box have 0 apples, and the third box has 5 apples, right? So if I view this problem in this way, then the problem reduces to how many different ways can I place two separators into these 5 apples, among these 5 apples. So it's basically reduces equivalent to arrange n indistinguishable apples and k minus 1 separators. Right? Because in order to create k different chunks, I just need k minus 1 separators. Right? For example, here, 2 separators will divide everything by 3 chunks. So I just need k minus 1 separators. Okay, this problem is equivalent to how can I arrange, how many different number of arrangements can we have among n indistinguishable balls and k minus 1 indistinguishable separators. Every different arrangement will give a different assignment of the apples to different boxes. Okay. So this reduces to the problem that we just considered here, right? We have T different types of objects. Each type have a certain number of objects in it. So here we only have 2 different types. One is the apples, one is the separators. Now we have n apples, k minus 1 separators. Okay, so how many arrangements? Well, we just first consider the total number of ordering, okay, by assuming everything is distinguishable. Then we just divide it by the permutations that we can have among each type. Okay. And this is exactly choosing n from out of choosing n out of n plus k minus 1. So it turns out this problem has a very simple result. So we just need to choose n out of n plus k minus 1. So this n plus k minus 1 denotes that in total we have this many number of positions. And I'm going to choose n positions to place the apples, place these indistinguishable apples in them. For the rest of positions, I'm going to place these separators. We have k minus 1 separators, so these separators will divide these apples into k different chunks, and for each chunk, I will assign it to a different box. Okay, first box, second box, third box. So by using separators, this problem can be understood in a very simple way. Now, follow-up question what if the balls are distinguishable? So we have distinguishable balls. Okay, each ball has a different label, and we have distinguishable boxes. Each box has a different label. Now I want to put these balls into these boxes. But now, compared to the previous question, because the balls are distinguishable, even if we put two balls in box 2, well, if we put 1 and 3, this will be different from putting 4 and 5, okay, in the box 2, because they have different labels. But in the previous, in this question, we don't have labels for the balls. So as long as you have two balls in box 2, they are the same. But here the labels, the balls are distinguishable, so the labels matters. So these two will be different assignment to box 2. The question is how many, now in this case, how many cases do we have? So if the balls are distinguishable, then we can just, we have to treat every ball separately, right? Because the first ball is different from all the other balls. Every ball is different from all the rest of the balls. So we have to consider this process one by one, separately for each ball. So we can think about this in this way. For the first ball, because the first ball is unique, it's different from the rest of balls, I have to figure out a box to place the first ball. So I have 3 choices, right, for the first ball. I can do 3 different choices. For the second ball, how many choices do I have? Once I place the first ball in the boxes, I don't care which box I place. Once I place it for the second ball, how many different choices do I have? Is there any restriction on this? Yeah, there's no restriction, right? For second ball, you can also put it to any box you like, and you have 3 different choices. So for the third ball, you have 3 different choices. So this gives you the result. So it's n, it's k to the power of n. Okay, so this is much simpler process. You don't. So in this case, because the balls are distinguishable, so we just need to assign the ball one by one. Right. Okay, so I think this finishes the lecture 6. Okay, and we still have one more problem to consider. Yeah. So when you do the homeworks and all the other combinatorial problems, you just need to figure out which of these questions that we go over today corresponds to the problem of interest. So you have, we're going to create an ordered list of lengths k. Now, how do we create that? So each position we can select from n objects with repetition. That means we have n balls, for example. With repetition means that if you select ball 1 and place it here, when you go to the second position, you can reuse ball 1. So you are sampling ball 1 with replacement. Okay, after you place ball 1, you're going to put it back into the box. So you can have repeated samples on different positions. So how many number of ordered lists can we create by sampling from this with repetition? Right. Basically, you can, because you are sampling with replacement. So every time, every position, you have n different choices. So first position, you have n different choices. And second position, again, you are sampling from this entire set. So you have n to the power of k, different number of ordered list. And I didn't print out lecture 7, but we can refer to the notes here. So this is a problem that we just talked about, n to the power of k. Okay, so here's an interesting question. The number of distinct functions that we can create from a domain of k different points. So the domain of the function, which is the x-axis, consists of k different points. And then the range of the function has n different points. And how many number of distinct functions can we create? Well, basically, for every single point in the domain, you are going to choose. In order to create a function, right, you have to assign a value to the function at this position. So for every single point in the domain, you have n different choices, right? And in the second point, you can also choose from these n different values. So in total, you have n to the power of k different number of functions. Okay. And you can have repetitions here because, for example, you can create a function that is a straight line, horizontal line, right? Over the entire domain, the function takes constant value. So this means that we can have repetitions in this example. Now the second question is more interesting. What if we restrict the previous question to one-to-one functions? Okay, what is one-to-one function? One-to-one function means that this is your domain, right? You have k different points, and this is your the range of the function. Assuming that n is bigger than k. One-to-one function is that for every point in the domain, you are going to link it to a certain point in the range, but they cannot be there cannot be repetitions in the range. So for every different point in the domain will be assigned to a different value in the range. They cannot have repetitions. So for example, this is not allowed. You cannot assign 2 to 2 because otherwise these two will share the same outcome. This is not allowed. Okay. You can only have distinct values for distinct inputs of the function. So how do we how do we approach this one? Well, because they cannot have repetitions, so we're going to start from, and these points in the domain, they are distinguishable, right? They are 1, 2, 3, 2k. They are different from each other. We can just start from whenever they are distinguishable, right? We should treat them in separately. So we start from the first point, and in total, I may have n different choices. I have n different choices to link to the first point. And once I go to the second one, because the first point is already linked to a certain point in the range, I only have n-1 choices left. Right. Once I go to the third point, the previous two has been linked to 2 different outcomes. So I only have n-2 choices left. Okay, and I keep going, so it's up to n-k plus 1 till the last one. So this is the number of one-to-one functions that we can create. And check. Right, this is this one. And it's just permutation. This is exactly permutation choosing k from n. But if you think about this problem differently, we just need to, among this set of n values, we just need to create we just need to select k different objects from this list, and then we need to order these different objects so that we can assign them to this distinguishable inputs one by one, one-to-one. So this is a permutation problem. So basically, every k ordered list that you create from this set corresponds to a one-to-one mapping. Okay. And this question, I think I will just go over it on the note. So what is the probability that at least 2 of n people share the same birthday? Assuming that everyone is equally likely to be born on each day of throughout the year. So this event is defined as at least 2 people out of n people share a certain birthday. At least. So it could be 2, 3, up to n people. These are different scenarios that belong to this event. So for this type of problems, whenever you see the event that is described by at least or at most, this kind of statements, we can always consider this complement, which is much simpler than this event. So the complement of this event is that everyone has a distinct birthday, right? Because E is at least 2 share a birthday. Its complement is that, well, everybody has a different birthday, right? But otherwise, you will have at least 2 people that share a birthday. And this is much simpler to analyze because in this complement event, everybody must be distinct, which is simpler, right? And from the probability law, we know that PE is 1 minus the probability of this complement. So if we can figure out the probability of the complement, we can figure out probability of E. And the nice thing is that this complement is very easy to calculate the probability, because the complement means everybody has a distinct birthday. Okay. And here's the thing. Because everyone is uniformly born throughout the year, right? Equally likely over 365 days, everybody is equal, and every birthday is equally likely to occur. So we can just consider all the total number of cases. So we have n people. The first people can be born over 365 days. The second people can be born over this many days. So this denominator corresponds to the total number of scenarios, the birthdays, right, of all these different peoples. And in the numerator, we need to look at the scenarios that everybody has a distinct birthday. Well, you start from first people, he or she may have 365 different birthday choices. And once you go to second people, because they have to be distinct, so he or she only have 364 now, right? And you keep going, when you go to the nth people, he or she will only have 365 plus 1 minus n different choices. Right? And this is the probability that of E complement. This is easy to calculate because here everybody is distinct, so it is relatively easy to calculate the number of assignments, right, of birthdays to different people. And then PE, now this is PE complement. Now PE is 1 minus PE complement. So it's 1 minus this big fraction number. And if you do a MATLAB, you can do a simulation on MATLAB to calculate how this PE looks like over different values of n. N is the total number of people that we consider. Well, you can see that PE is almost 1 once we have about 60 people. So if you have 50 people, then this event may occur with 97% of probability. If we have 60 people, we have 100 people, it's very, very close to 1. So basically for every 50 person, most likely there are at least 2 persons that share a birthday. Okay, so this is a very common event in practice. You consider the students in your class. We have 20 students, we still have 20% of probability to to have two people that share a birthday. Okay, I think you can now start working on the homework 3, should be covered by these materials.